When we talk about fundamental identities in trigonometry, we're actually talking about some identities that we're already familiar with. We'll be adding some identities to the list as well, but let's go ahead and get started with the reciprocal identities. Now, the reciprocal identities, like I said, we've actually worked with these before, but we're going to put a lot of these identities in one spot so we can start using them to establish identities and some other work where we can solve triangles and solve for unit circles. Now, when I talk about an identity is something that is true for no matter what value that you plug into it. So it's an equation that is satisfied by every value in the domain of the variable. So to get started with the reciprocal identities, for instance, we know that the cotangent of theta is the reciprocal of tangent, so that would be 1 over tangent theta. Now this would be true for any angle theta that we could plug into here. So this is an example of the reciprocal identity. There's also one for secant. Secant of theta is 1 over cosine of theta. And then of course our other one is cosecant of theta is 1 over sine of theta. So those are our reciprocal identities, and we already know these. We've already worked with these before. We also have the quotient identities, and these quotient identities are the same as any identity, meaning it's true for any value in its domain that we can plug in here. Tangent of theta, we already know, is sine over cosine. And because cotangent is the reciprocal of tangent, then we also know that the cotangent of theta is cosine theta over sine theta. And we'll want to keep these memorized and familiar because we use them so often. So it's a good idea to start a note card and put all these identities on. We also have the Pythagorean identities, and we've already worked with these. In fact, we had a problem on our last exam that it asked you to establish a Pythagorean identity. And there's 3 of these. Now the cool thing about the Pythagorean identities is if you can memorize one, you'll have the other 2 by just dividing through by either sine squared or cosine squared. So our first Pythagorean identity is sine squared theta. And remember, always put parentheses around the arguments of your trig functions. My math lab doesn't do that, and sometimes it gets a little bit confusing, so make sure that you guys are doing that. So sine squared theta plus cosine squared theta is 1. Another Pythagorean identity is tangent squared theta plus 1 is equal to secant squared theta. And our third Pythagorean identity combines cotangent and cosecant, would be 1 plus cotangent squared theta equals cosecant squared. Okay? Now, just because we have one of these Pythagorean identities, let's say sine squared plus cosine squared equals 1, it's not only just good for that, it's good for also solving for cosine squared. For instance, we could solve that one for cosine squared, and I get cosine squared is equal to 1 minus sine squared. So even though these identities are here, they're not just good for exactly what we have them solved for. We can also use it for several other things as well. Let's also look at the even odd identities. We talked about the even odd identities when we were working through the graphs of each of the trig functions. So the even odd identities. And for the even odd identities, the sine of negative theta is equal to negative sine theta. Okay, we also know then that the reciprocal of sine is cosecant, so this same thing is true for cosecant. Okay, so that takes care of 2 of these. And this is also true for tangent, because remember, tangent is sine over cosine, so it follows the rule for sine. So tangent of negative theta is equal to a negative tangent theta. And the cotangent follows along with tangent is equal to a negative cotangent theta. So these all kind of fit together. And then over here on this other side, then we would have cosine of negative theta is equal to just the cosine of theta. There's no negative sign in front. Okay, and then the reciprocal of cosine is secant, so we would know that the secant of negative theta is equal to just the secant of theta. Now these are called the even odd identities, so it would be nice to know which ones are even and which ones are odd. So let's go ahead and have a look at these even functions. So these are the evens with the cosine, and then the tangent, the sine, the cosecant, the tangent, etc. These are the odd identities. So again, it would be a good idea to have these on a note card and to refer to them often, and the more you refer to that note card, the sooner that you'll have these memorized. So let's go ahead and start looking at some applications of some different types of problems that you could see here. And I'm going to be pulling these from my math lab, so you'll see the same exact setup for your homework problems here that we're working as you will in my math lab. Okay, so let's go ahead and it says use identities to find the exact values of the trig functions. And in this case it's alpha, and it asks us to rationalize the denominator. Now they give us some information about tangent, and they also give us the information that we're in quadrant 4. So let's go ahead and keep that information in mind. So here we are in quadrant 4. So in quadrant 4 we know that the cosine of alpha, and they're using the letter alpha here, so that's why we chose that, is positive. And because cosine is positive, that tells us that secant is positive. And sine in the fourth quadrant is negative. So that means the cosecant is also negative. And then they already told us that tangent was negative, but we would know that as well. But we'll write it down here. And because we know tangent is negative, we would also know then that cotangent is negative. So before we even really get started here, we already know all of this information about alpha because we know it's in the fourth quadrant. So it's important to establish where you're at first, and then after you establish where you're at, you can talk about the sine and the cosine of all the different angles. Now there's several different ways to solve these problems. Sometimes we could use some unit circle information, sometimes we could use the right triangle trig. So we're starting with the tangent of alpha equals negative 1/6. Okay, so if we think about this, I should be able to think back, tangent is y over x. I could also think tangent is sine over cosine. I could also look at this in terms of a right triangle in the fourth quadrant. So there's several different ways that we could solve this. I'm going to use the fact that we know for a circle with the center at the origin, the equation of a circle is x squared plus y squared equals r squared. And that's something that we learned a while ago. And if I plug in this value for y and x, I should be able to solve for r. So the negative sign usually goes with the top. And because we're in the fourth quadrant, it makes sense that the y would be negative. But even if we weren't in the fourth quadrant, we probably wouldn't want to put the 6 with the negative. When we square it, it doesn't end up mattering. So here I'll have 6 squared plus a negative 1 quantity squared equals r squared. So 36 plus 1 is r squared. R squared is 37. Now remember, r is a radius. So I don't really care about whether it's positive or negative. I care about whether the trig functions are positive or negative, but r is going to be positive here. So from here, this is the information that I have. I'm in quadrant 4. So in quadrant 4, that means my x value will be positive, my y value will be negative. So 6, negative 1, and then I also have that r is equal to the square root of 37. So x is 6. Y is negative 1, r is the square root of 37. So when I find all my other trig functions, this should go pretty quick. So let's start with cosine. So the cosine of alpha is x over r. X in this case is 6. R is the square root of 37. So this is 6 square root of 37 over 37. So remember to rationalize that denominator. Now because I know cosine, I should also be able to figure out secant pretty quickly because it's the reciprocal. So the reciprocal here is r over x, or the square root of 37 over 6. Now this doesn't need rationalized because we only rationalize what's on the denominator when they're radicals in the denominator. Okay, let's look at sine. Sine of alpha is y over r. Y in this case is negative 1. R was the square root of 37. And of course we'll want to rationalize that. So I get negative square root of 37 over 37. And because we know sine, we should be able to figure out cosecant fairly quickly. That's the reciprocal, so it would be r over y. Again, r in this case is the square root of 37. Y is negative 1. We usually don't leave the negative in the denominator. We usually put it up top or pull it out front. So in this case, we could just say it's negative square root of 37 because dividing by 1 in that denominator really makes no difference. Now the last two were already given that tangent was negative 1/6, so that was given. And then from here, I know that the cotangent is the reciprocal of that, so it would be a negative 6. Now it's not a negative reciprocal. I don't change the sign, I just flip the fraction. So that's an example of using your trig identities, using those reciprocal identities to figure out all the values of the trig function. Now in order to do this, you need to be given some information about the trig functions and enough information to figure out which quadrant you're in as well. Let's go ahead and look at another problem. So for this one, we're given that the cosine of theta is negative 1. So the cosine, I'm going to put parentheses around the argument of that trig function, is negative 1. So then it's asking me, what is the cosine of negative theta? So we technically don't know what theta is. And they want us to be able to find the cosine of the negative value of theta, just given the fact that we can use our even odd identities. Now do recall that cosine was an even function. And so it's an even function. So what we know then is that the cosine of negative theta is equal to just the cosine of theta. So the cosine of theta is negative 1. That would imply then that the cosine of negative theta is the exact same thing using this even function. It's saying it doesn't matter whether the argument is positive or negative. Okay, they're both going to have the same output value. Now we know something about this cosine of theta equals negative 1. This would be something like the cosine of pi is negative 1. And then if we negated pi, we'd get negative pi, and the cosine of negative pi is also negative 1. So this is an example of how that might work. So when you're working through these problems, a lot of times they're not going to be so simple as, gee, I recognize what tangent that is, or I recognize something about that angle. But in this case, we were able to do that and kind of double check things. Let's go ahead and look at one that does involve tangent. So it says use identities to fill in the blank. So what we know here is that the tangent of theta is 5. So we are going to use a reciprocal identity. And the reciprocal identity that we could use here is to relate this tangent to this cotangent, is we know that the cotangent of theta is equal to 1 over the tangent of theta. So again, the cotangent of theta is 1 over the tangent of theta. It's one of our reciprocal identities. So the cotangent of theta is 1 over the tangent of theta. But we know the tangent of theta is 5, so this would be 1/5. Now, make sure you read the directions on this, because the directions might say leave this in fractional form, or it might say leave it as an integer. So if it's in fractional form, we'll leave it as 1/5, but if it says to leave it as an integer, I can't do that because 1/5 is a fraction. It also might say leave it as a decimal. So this would be fraction form, this would be decimal form, and you just need to make sure that you read the instructions when you're working through the problem in order to figure out exactly how they want you to have your final solution. Okay, let's go ahead and look at a few others. I think for the most part these will be pretty straightforward if you have your identities written down on a sheet, because once you have those identities written down, you can usually simplify these. Okay, let's look at this other one. It says use identities to fill in the blank. Sine of theta is 7/8. So we have the sine of theta is 7/8. And sine is an odd identity, or an odd function, I should say. So what that ends up looking like is the sine of negative theta is equal to a negative sine of theta. And they want us to figure out what negative sine of negative theta is. Well, if I multiply both sides through on this side by a negative, or if I divide both sides by a negative, however you want to look at that, I end up with negative sine of negative theta is equal to the sine of theta. So that tells me then that the negative sine of negative theta is equal to the exact same value. So this says whatever sine of theta is, that's the same as negative sine of the negative of the angle. So you can use these identities to simplify expressions quite a bit, and they're pretty straightforward from here. Again, when you're simplifying, you need to always make sure you put parentheses around the arguments of the trig functions, because if we had something like sine negative theta, that would be kind of confusing. Does that mean to take sine and subtract theta and there's no argument on the sine? Or does it mean to take the sine of negative theta? So just make sure when you're working that you always do put parentheses around the arguments of those trig functions. It will make your work a little bit easier to look at and to work with while you're solving questions. So this one we're given the cosine of negative alpha, so let's go ahead and start with that. The cosine of negative alpha is equal to 6 square roots of 37 over 37. And we're also told that the tangent of alpha is positive. So this is giving us the information about the cosine of negative alpha. Well, recall that the cosine is an even function, and because the cosine is an even function, let's write out this off to the side here. I can rewrite this. So the way that that would rewrite is the cosine of negative theta is equal to cosine of theta. So what I could do then is I could take this and rewrite it as just the cosine of theta, or sorry, alpha. We're using alpha as our variable. 6 root 37 over 37. Now that compares directly now to the tangent. Now see, this was a negative alpha and this was a positive alpha. Now I can compare these directly. So what this is saying is the cosine is positive and the tangent is positive. So that means I'm in quadrant 1. Now what we're asked to do here is just to find the exact value of the sine of alpha. We don't need to find the other trig function. So one thing I know here is in quadrant 1, the sine of alpha is going to be positive. So a quick one that we could use here then is one of our Pythagorean identities. Sine squared plus cosine squared equals 1. So sine squared of alpha plus cosine squared of alpha equals 1. Now I know what cosine of alpha is. That's going to be 6 square roots of 37 over 37. And it's going to be all of this squared, not just the numerator, not just the denominator, but the whole fraction. Now if I solve here for sine squared, I'd get sine squared of alpha equals 1 minus, and if 6 times 6 is 36, square root of 37 times the square root of 37 is 37, and the denominator then would be 37 squared, which is 37 times 37. Now 37 divided by 37 is 1, so I'm left with sine squared alpha is equal to 1 minus 36 over 37. Finding a common denominator, I have sine squared alpha equals 37 over 37 minus 36 over 37 equals 1 over 37. So again, sine squared alpha is equal to 1 over 37. Now I don't need to know what sine squared is, I need to know what sine is. So the next step I would take is to take the square root of both sides. And I'd have the sine of alpha equals plus or minus the square root of 1 over 37. Now let's think about simplifying this a little bit. We know we're in quadrant 1. And because we're in quadrant 1, I know that the sine of alpha is positive. So I know I'm going to use the positive here. Now in the numerator, the square root of 1 is 1. In the denominator, the square root of 37 is just root 37. And then I'll rationalize it. So finally, I get the sine of alpha equals the square root of 37 over 37. And because I'm in quadrant 1, that's positive. So you can see where we can use a Pythagorean identity in the fact that the cosine function is even, and knowing where my quadrant is to solve and work through this. Now again, when you're working with the identities from that list that we had at the beginning of this, they're not always good for just the one form that they're given in. A lot of times we can rewrite them in different forms. So this one says choose the correct expression that completes the identity. Well, let's go ahead and start with one of my Pythagorean identities, and that would be secant squared involved would be 1 plus tangent squared is secant squared. And they're using x for our variable here, so let's use x below. Now, I could look at this and I could say, well, the only thing this is good for is if I know what 1 plus tangent squared is. But what I could do here is I could solve this for 1 minus secant squared. So if I did that, I could subtract secant squared from both sides. And then what I would be left with then is 1 minus secant squared plus tangent squared equals 0. Well, this isn't quite what I wanted. I wanted just 1 minus secant squared alone. So the next thing I would do is subtract the tangent squared of x to both sides. And of course, as always in algebra, whatever you do to one side, you have to do to the other. These would cancel and I'd be left with 1 minus secant squared of x equals negative tangent squared of x. So up here, this would be equal to a negative tangent squared of x. So again, we can use the Pythagorean identities, and we don't always have to use them in the form that they're given to us in, but you can use them to rewrite. Let's look at another one. And on this one, again, we're using these to rewrite. Okay, it's not letting me copy that. Just a second. Okay, so here we go. This one says write the trigonometric function in terms of the second trigonometric function. So we want to take secant and we want to write it in terms of the second function. Well, I think that the problem that we just worked would be a good place to think about starting. So let's think about secant and tangent being related. If you think about all of the identities, our quotient identities, our reciprocal identities, the only one that relates those two is one of the Pythagorean identities. Now the Pythagorean identity that we want to look at is 1 plus tangent squared of theta equals secant squared of theta. So write the first trigonometric function in terms of the second. So we could take this and we could say, okay, well, secant squared of theta is equal to 1 plus tangent squared of theta. So I almost have it already. I don't want just secant squared though, I don't want just plain old secant. So what I'll do from here is I'll look at this and I'll think, okay, so how could I get that down into just a secant? Well, what we could do is we could take the square root of both sides. And the square root of secant squared is secant. Now when I take the square root, remember I don't know what quadrant I'm in here, so I need to include the positive and the negative, so plus or minus square root of 1 plus tangent squared of theta. So this is how I could rewrite that in secant in terms of tangents. So when we talk about rewriting these, you need to keep in mind that when you take the square root, I have a positive and I have a negative root, and I need to know where I'm at in terms of first, second, third, or fourth quadrant. If you don't know which quadrant you're in, you have to include both the positive and the negative. This next problem that we're going to look at gives us some good advice. And it says, write the expression in terms of sine and cosine and then simplify so that no quotients appear in the final expression. So what they'd say is to rewrite everything in terms of sine and cosine. So let's start with that. Now 1 minus secant squared. Well, 1 minus secant squared, if you recall, that is equal to a negative tangent squared from the problem that we just did up here. So that was from right up here. But if you don't recall that, what we could do is we could rewrite it as 1 minus 1 over cosine squared of x. Or sorry, theta. We're using the variable theta here. Okay, so again, secant is 1 over cosine. Then our next step from here would be to find a common denominator. Let's think of this as 1 over 1. So this would be cosine squared of theta over 1. Multiply top and bottom by cosine squared of theta over cosine squared of theta. Anything divided by itself is 1. Minus 1 over cosine squared of theta. And then I still have this cosine squared of theta over 1 out front. And then I can rewrite this as a single fraction. So this would be cosine squared of theta minus 1 all over cosine squared of theta. Now there's a couple things that we could do here. First of all, I see that the cosine squared on top and bottom would cancel, leaving me with cosine squared of theta minus 1. Now cosine squared of theta minus 1 is going to be equal to a very familiar trig function. Using one of our Pythagorean identities, we should be able to come up with that to be a negative sine squared theta. Okay, and so that would be our final answer here. But let me show you how that works. So how do I move from here to here? I can't just write it down. I need to justify it. And on your exam, make sure you do the same thing. Make sure you always justify your work. So from the Pythagorean identity, if you recall, we know that sine squared of theta plus cosine squared of theta equals 1. So if I tried to get cosine squared minus 1, I'd subtract 1 from both sides. So here I'd have sine squared of theta plus cosine squared of theta minus 1 equals 0, because 1 minus 1 is 0. But I want cosine squared minus 1 by itself, so that my last step would be to subtract sine squared from both sides. So over here they cancel, and then I'm left with cosine squared theta minus 1 equals negative sine squared of theta. So that's where that negative sine squared of theta came in. Now a quick note, if we looked at cosine squared theta minus 1, does that equal cosine squared of theta, just the angle theta, and then subtract 1? I don't know. So always make sure that you put the parentheses around the arguments of your trig function to clarify that, because if it's on a test or a quiz and I'm not sure what you mean, I'm going to assume that you don't know which one you mean, and it will get counted incorrect. So always put parentheses around the arguments of your trig functions. It's a really good habit to get into, and it'll be really important for your upper level math classes as well. So this one again gives us some good starting advice. It says write the expression in terms of sine and cosine and then simplify so that no quotient appears in the final expression. Well, our first part here is already written in terms of cosine, so I'm going to leave that as is. I'm going to put it in brackets over a fraction though. Now for our second one, I'm going to have 1 over 1 plus secant, if you recall, is 1 over cosine of theta. So that would be one way that we could get this started. Another thing that we could do is I could rewrite this as two separate fractions as well. So this could be 1 over 1 minus cosine theta over 1. Now from here there's several different things that we could do. I would like to think about foiling this. Remember from multiplying two binomials, first outside, insides, and lasts. So I'm not going to simplify this at all. I'm going to write it out just as is. So this would be 1 over 1 times 1 over 1. So that's the firsts. The outsides would be 1 over 1 times 1 over cosine theta. That's the outsides. And then I'll have the insides. That would be a negative cosine of theta over 1 times 1 over 1. So that's these two inside pieces right here, plus our lasts. Now my last would be a negative cosine theta over 1 times 1 over cosine theta. That would be the last. So FOIL, first, outside, insides, and last. So let's go ahead and simplify this now. Of course, this first term simplifies to 1. The second term is 1 over cosine of theta. This third term is minus cosine of theta. And then this last term, the cosines cancel, and I'm just left with a minus 1. Now from here, the positive 1 and the negative 1 cancel. And then 1 over cosine is secant. So this would be secant theta minus cosine theta. Now let's go ahead and look at our directions. It says so that no quotients appear. And again, we have no quotients here. There's no fraction. So this is simplified completely. Now sometimes it's hard to know if you're simplified completely. But here, if we went back to rewriting secant in terms of 1 over cosine and then found a common denominator, I'd actually be working backward right toward my original problem. Now sometimes you can graph almost all the time, you can graph both sides of an identity to see if one side is equal to the other side, meaning the graphs are the same. So let's go ahead and look at a problem where we're using a calculator to determine whether we have an identity or not. So when you're using your calculator, a couple quick things that you do need to know how to graph, because we're going to be graphing these. That's how we'll solve these. And we also need to be aware of what the argument of the trig function is. And then we also need to know what we're looking for. And basically we want to graph the left side, we want to graph the right side, and when I graph both sides it should be the exact same picture. So this would be the cosine of 2x equals 2 cosine of x. Now it says use a graphing calculator to make a conjecture as to whether each equation is an identity. So we're wondering, is this true? Is this a true or a false statement? So there's a couple different ways that we could approach this. So if we're trying to use a calculator to determine whether something is an identity, we need to keep in mind that the graph on the left side and the graph on the right side should be exactly the same if it's truly an identity. If they're not the exact same graph, then it's not an identity. So let's go ahead and graph first cosine of 2x. So again, cosine, I want to make sure that the 2 and the x are both in the parentheses. And if I want to, I could graph that. Notice that's the blue line right here. Let's go back to y equal. Let's go to our second line and let's graph 2 cosine of x. So we're going to figure out if this is an identity, like one of the Pythagorean identities or something. Now the blue graph was my original, that's the left side. The right side is the red graph. So let's go ahead and graph these. These are not the same graph, these are very different graphs. So I would say this is not an identity. So let's go ahead and paste in the information here. So this is what we're graphing. Again, the blue is on the left. Red is on the right. Okay, and let's look at the graph. The graph in this case was very different as well. We should see something that is exactly the same for both the blue and the red, meaning one graphs right over the top of the other. So if we look at these are very different graphs. So this would not be an identity. So this would be not an identity. And it's not an identity because when we graph these, the graphs are different. Okay, so I think your option in my math lab when you're doing a problem like this is to say yes or no. So this one we would definitely say no, not an identity. Let's go ahead and look at our next problem. And again, we're trying to establish identities again. And when we try and establish an identity, sometimes they give us some direction about whether we should use the graphing calculator or we should rewrite in terms of sine and cosine. But the ones they give us about graphing calculators, you usually have to use that because we don't have enough other identities yet in order to establish that. So let's go ahead and look at this one. And see if this one's an identity. So this one they tell us to use a graphing calculator, so we'll use our graphing calculator again. And so what we want to graph is the left side and the right side and then compare them. So on the left hand side I'll have the graph of the cosine of 2x. And what I'm trying to figure out is this equal to the right side, 1 minus 2 sine squared of x. Now up here, when we were working, what we did is we tried to figure this out. It was not the same graph for blue and red, so this was not equal, and because it was not equal, they were not identities. Okay, so let's go ahead and pull our calculator in, and let's graph the left side and the right side. So we'll go to y equal, we'll clear out our last graphs. Okay, so this would be the cosine of 2x. So we can graph that one, it's blue. Okay, now let's go back and graph on our red line, our second line, 1 minus 2 sine squared of x. Now, I want to show you something here. I can't put a squared sign right here. So after I put in the sine the parentheses pop up and I can't put the sine squared in of here. So we have to be really careful about how we write this. If you wanted to be really specific, you could just write sine x times sine x because that's sine squared of x. Or I can show you exactly how to rewrite that using your squared symbol here in a second. And to me, I don't like how the calculator does that. It's a little bit confusing. So let's write that as, instead of sine squared, let's write it as sine times sine for now. And if you notice, the red graph traveled right across the blue graph. Okay, so let's go ahead and regraph that. So let's go second quit. We'll go to y equal, and we'll go to graph again. So again, the blue graph was there, and then the red graph traveled right on top of it. So it was kind of hard to see because once the blue graph was done, the red graph went right over the top. So let's go ahead and paste that graph over here. And we can see here we caught the blue graph being done and then the red graph copying right over the top of it. Let's also include exactly what we were graphing. That would be under the y equal. And because these are equal, this would be an identity. So again, these are identical graphs. One is graphing right over the top of the other. And because one is graphing right over the top of the other, then this is an identity. This means it's true for any value that we plug in. For in this case x, any value in the domain of those functions. So these are examples of using your calculator to determine whether we have something that's an identity or not. And this is actually an identity that we could use to solve other problems as well. So as usual, if you have any questions, let me know. These are pretty straightforward if you start putting things onto a note card, so you'll have all your identities in one place. It'll be very, very helpful for you. Good luck.